Good morning, everyone. Hello, hello, hello. Anyone have any questions while we're waiting for other people to come in? We're currently working on chapter 17. I suspect I'll finish it today. And we'll jump into 18. Everybody good? Looks like they are. We got 13 of you souls up in here. I love it when old white people try to be cool. I didn't change the date for chapter 20 homework. Well, let me do that right now while I'm on there. Oh yeah, chapter 20. I haven't even done it yet. No problem. Yeah, I don't usually set that yet. But that'll be maybe the last chapter we get to cover. I'm not sure. I hope it's not. I hope we get to do the 2 chapters in quantum mechanics. So they might actually be due at the end of the like 12:15 or something like that. Chapter 17 homework. If it's due tomorrow, I'm going to change it to being due Sunday, just because I don't think I'll finish chapter 17 till today, and I think I should have more time. Now, if it's the concepts, I think you could finish the concepts by tomorrow, but not the physical problems, or the actual mathematical problems, I should say. So I will check that. I'll make a little note here, because turns out when I don't make notes, I don't remember stuff. So chapter 17. And then I'll also put a note about chapter 20, mastering. Okay, so I'll do that after this. Anybody have any other questions? Test for 27-28 didn't affect the Canvas grade. Yeah. I was told by another student that it's not in the proper category, so it must have made it as something other than online tests. So I got to go back and fix that. If you expected your grade to go up, make a note of what it is now, and I'll check and see if the actual grade wasn't counting properly, and then I'll put it in the right column, and then that should address it. So you can tell whether it goes up or down. Okay, it looks like all the questions that people have chatted to me. Anything else? Everybody able to get their test done on Sunday? Remember, we got another test due tomorrow, so let's don't forget that. Hopefully everybody got their test done on Sunday. Did you have any problems finding that test? In one class, evidently I didn't make it available in the online test section, but luckily the student saw it in the grade book, and you can like click on the grade book and it'll let you take it from there. I didn't realize that. Another student found it, some other deep bowels of Canvas that I didn't know existed either. The lab makes no sense on how to do it or what to do. There are places where you can't even fill in data. I'm even trying to remember what lab we're doing this week, or what lab we did last week. You remember, Clarence?
The waves.
Oh, okay, the waves one. Yeah, that's the one with the microwaves and the red laser. Yeah, let me get a look at that, and maybe I can send y'all some advice. If worse comes to worse, if y'all are having problems with it, I'll give you an extension on turning it in, and we can talk about it at lab time. But I'll see about if I have time at the end of class today. I might not, because there's a class right after it. But other than that, we can still make a Zoom appointment if you want, so we can have sort of some private help. That's fine. If I do that, I'll announce it to everybody, unless someone needs specific private help, just one-on-one, in which case I will announce it to everybody. So we can always do that. All right, so let's move on to chapter 17. When we last met, I went through the different temperature systems. I told you a little poem, if you will, or mnemonic that you can use to remember the Celsius system. And then I told you the way that instructors have learned that's probably more beneficial on how to convert between Celsius and Fahrenheit, by realizing that boiling point and freezing points are equivalent in the two systems, but different numbers. Therefore, if you just find the difference between the temperature you have and the temperature of freezing, or the temperature you have and the temperature of boiling, then you just use the ratio 9-to-5 or 5-to-9 to figure out how far away you are from freezing or boiling on the other scale. and then add the freezing or boiling point temperature back in. So that's kind of a nice way of going back and forth. And that's something I usually can do in my head. Sometimes you just have to make it, 1.8 versus 1, because that's another version of 9/5. 18/10. Of course, when you divide 18 by 10, you get 1.8. So you get 1.8/1 is another one. So that's kind of nice. You either divide by or multiply by 1.8, and life is golden. Then I actually used the typical y equals mx plus b scenario to derive the equations for it. I told you about how length contracts and expands upon heating, contracts upon cooling, and how volume does the same thing. So now I thought I'd work a couple of examples showing that stuff and introduce you to the ideal gas law, which you might more than likely already know, and then introduce you to another version of the ideal gas law, which you wouldn't necessarily know unless you've had a physics course before. So it's just a one with a different constant, and that comes in real handy later when we're studying kinesia, or I should say kinematics, or not kinematics, or kinetic theory. I know there's a word in there that starts with K. I just got to find the right one. So, all right. So let's go ahead and start on our examples. Any last questions? May God have mercy on your soul. All right, here we go. Sorry, I'm in a giddy mood today. All right, so our first example, I will call this, ironically, example 1. Today is 11/16/21, and this is PHY 242 D01B. And example 1, I have a 100-meter concrete beam at 20 degrees Celsius, and I wish to know its length at 37 degrees Celsius. Okay, and that's really out of focus. Let me do it. That's better. So I want to know that. That's the big question. So how long is it? And this will make some sense because you've probably seen or even felt the bumps that are expansion brakes on concrete bridges as you're riding across. You got bump, 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 bump. That's what those are for. They every certain distance they give a little gap so that it can actually safely compress against the other side without shattering. Because obviously bridges with ginormous holes are somewhat problematic and less than ideal. So, so what is the final length? So our equation says that delta L over L0 is equal to alpha delta T, where alpha is the linear expansion coefficient for the particular material. This particular material is concrete, which has a linear expansion coefficient of 12 times 10 to the -6. So alpha for concrete, which I'll write CC, is 12 times 10 to the -6 reciprocal Celsius degrees. I can change this around by saying L minus L0 is equal to L0 alpha delta T, and then I'd get L is equal to L0 times 1 plus alpha delta T, and that's the equation that's most useful in this scenario. So I'll say L is equal to 100.0 meters, and I'm actually only specifying that so you'll see that the 100 is full Sig Figs. And then 1 plus 12 times 10 to the -6 reciprocal Celsius degrees. I'll make this a square bracket now. And then times the change in temperature, which would be 37, which I'm going to call 0.0, just because I like to have 3 Sig Figs there. So 37.0 minus 20.0 degrees Celsius. Let's just pretend I wrote that up there because I'm infallible and everybody knows I didn't really make a mistake. So except for all the times I did, right? All right. So when you do this calculation, it turns out you get a not a very impressive number. In fact, you get something along the along the lines of 1.0, or excuse me, of 0.00102 or some god awful mess like that. So this quantity right here, just the multiplier, not the actual original length. This thing, this pen evidently is not alive. This quantity right here is like 0.00102. So you can see it's not a huge change. And of course, you're going to add 1 to that, and you're going to multiply it by 100. And when you do get that, you get 100.0204 meters. Now, technically, when I subtract 37 minus 20.0, I get 17.0, which is 3 sig figs, but this is only 2 sig figs. And then that's 2 sig figs way down the 10th decimal place. This 1 is an infinite number of decimal places. So that, in that sense, sort of brings it down to a huge number of decimal places being significant, 10 times 100. But really the main point here that you see is that you're going to be off by about 2 centimeters. And that's about the distance across those 2 nails. And that's comparable to the expansion breaks you see in the bridge. So I think that's not an unreasonable result. Does that make sense to everyone? Pretty straightforward problem, right? The volume formula is used exactly the same way. Delta V over V0 is equal to alpha delta T, except instead of alpha, they have a beta. And it turns out experimentally, I kid you not, that alpha is the one-dimensional thing. If you did a surface area, you get a sigma, and that's a two-dimensional thing. And if you did the volume, that's a three-dimensional thing. And lo and behold, beta is about 3 times as large as alpha. So that's kind of nice to keep in mind. But there's one example. Let's do another. So in this case, I want to fit a ring over an actual rod, and I want to take it as being gold, just, you know, so we have some information about gold. So let's imagine taking a ring and its radius happens to be, let's treat it more or less like a wedding band. So in that case, I'm going to say its radius, well, actually, no, it's not treat it like a wedding band. Let's treat it like a, I don't know, a bracelet, because evidently I forgot to divide the radius by the diameter by 2 when I was making up this problem. So we're going to say of a wedding bracelet or whatever. So that actual ring is going to have a radius of 2.189 centimeters. Okay, notice I'm going to the thousands. So this is like caliper measuring everything. And I'd like to fit it on a rod whose radius is 2.201 centimeters. But oddly enough, when you go to fit something on something else, it's not sufficient for this to just be that big. It's still not going to fit. You're going to have a little bit of play. And I'm going to say that the play, our play, is 0.009 centimeters. In other words, this ring has to be expanded so much that its radius becomes 2.201 plus 0.009. Okay. And what I want to know is if it's initially at 20 degrees Celsius, so T0 equals 20.0 degrees Celsius, what temperature will I have to bring it to be large enough to fit? So T final is question mark. So I've given you all the symbols and explained it in words, but basically what I'm saying is, hey, I have a ring 2.189 centimeters in radius. I want it to fit on a similar gold rod, 2.201 centimeters. But in order to do so, I have to have an extra 0.009 centimeters bigger than that rod in order for it to fit. What final temperature must I raise this gold ring to? Now, the rod could be made of anything, but what we're trying to do is warm up the ring to make it expand, and not warm up the rod, or we're going to be right back where we started from, right? Especially if they're the same material. If you warm up by the same amount, they're going to go up by the same amount in both cases. So one thing you got to realize is, yes, it is true that if you have a hole in something, so this is like one of your conceptual questions in the book. If you have a hole in something and you heat this plate up, what happens to the actual hole? Does it get smaller or bigger? Because in reality, this formula says that sort of every dimension seems to get larger. So you might want to make the argument that right here, this little stretch from here to here, getting larger would make this radius get smaller, but that's not the case. Okay, so keep that in mind. It actually, the hole acts just like the metal would if the metal was inside it. So if you put the metal inside of it, pop it out, heat it up, you'd see that the ring would get larger, the actual cylinder would get larger. So this hole is going to act the same way. So that's why I knew I had to increase the temperature. So what I want now is I want to figure out what's the new temperature. Well, we know that delta L over L0 is equal to alpha delta T. And that's really nice because in that form, it's really easy to solve for delta T. You say delta T, the change in temperature, has to be equal to delta L over alpha L0. Well, delta L is actually 2.201 centimeters plus 0.009 centimeters. Now I'm literally saying the radius has to increase by that, so the diameter has to increase by double that. I'm not making a mistake by doing that. That's just what I'm making the claim of. It's probably a little much, to be honest with you. Maybe a more reasonable figure might have been 0.003 or 0.004 for this, but either way, we're just going with the problem as it's stated. So that's the final radius of this thing. And the initial radius was 2.189 centimeters. Notice I don't care about it being in centimeters because we're going to divide it by centimeters too. So in the end, the answer is still going to be no units over alpha. So now I'm going to take for gold. Gold happens to have an alpha equal to 14 times 10 to the negative 6 Celsius degrees to the negative 1 power. So I'm going to say 14 times 10 to the negative 6 Celsius degrees to negative 1 power. And then L0, of course, is the 2.189 centimeters. And what you end up getting when you do this calculation, and y'all should verify this, I got 685.2 Celsius degrees is the change in temperature. So let's check out the Sig Figs. This is going to be 2.210 minus 2.189. So we're really getting a whole number plus 3 decimal places. And then we're multiplying 2 decimal places times 4 by 4 digits. So I only got 2 down here. So really, I should only be carrying this to the 2-digit mark by Sig Fig rules. Okay. So I'll keep calling it 685, but like I said, I carried an extra digit. All right, so that's the change in temperature. So that means the final temperature, which is what we're really asked for, T final would be 20 degrees Celsius plus 685.2 degrees Celsius. Whoa, I just made a big zero out of the C. Okay, so this is going to be on the order of 705 degrees Celsius. Now you might say, wait a second, that's gold. That's pretty darn high. So what's the melting point of gold? Well, it turns out the melting point of gold, T melting point for gold, is actually not that close to it. It's 1064 degrees Celsius. So we're okay. So you could actually heat that up. I wouldn't advise picking it up after heating it up to 705 degrees Celsius. But certainly it's not anywhere near starting to melt. But so with that in mind, we can actually perform that experiment. Isn't that great? Any questions on that? So that's just 2 typical problems. You can find some more in your book. Some are actually, I think there's one just like this one in your book, the concrete one. And oh yeah. I think I remember Giancoli actually had a ring and rod scenario as well. So I probably just made up problems very similar to the ones that Giancoli had. All right. So with that in mind, you can see those 2, and you can see some other ones. I think Giancoli has one on a gas tank, which is kind of fun to do. And it also has questions that are conceptual in nature that I think are really worthwhile. That's why I took time to explain to you that a hole in a material acts just like the material if the material was there. So you can certainly know that when you pull out the disc of metal and heat it up, it's going to get wider. So this hole should get wider as well. All right. With that being said, let's get into the ideal gas law. So it turns out that over time, people put together these various laws. One of the first ones, of course, was Boyle's law. And Boyle's law is also called the scuba diver's law. Well, by scuba divers it is. But basically, the number one rule in scuba diving is never hold your breath, never hold your breath, never hold your breath, right? And the reason why is Boyle's law, because Boyle's law says that pressure and temperature, or pressure and volume, are inversely related. So what that means is as the pressure goes down, the volume goes up. So as you ascend from some depth in the ocean, say, to some lesser depth, the pressure on you decreases. So if you were holding your breath, the volume of the air inside of your lungs is going to increase, and that could lead to your lung popping. And a popped lung is called an arterial gas embolism, and it's less than pleasant. I would advise you not taking on such a risk. And sadly, you can actually do it depending on the health of your lungs and age and stuff like that. You can do it as little as 3 feet. So even, I mean, it's hard to, but even being on the bottom of a 3 foot, out of above ground pool and coming up after taking an air full of a lung full of air from a bucket, say, would be enough to actually cause your lung to pop. So don't do that. It's bad. Okay. But this should make sense. Obviously, when the pressure that's squeezing the thing gets bigger, then the volume is going to get smaller. So that should be a common sense sort of law, and it's called Boyle's law. And I very seldom remember these, so I always take the time to point them out again and look them up again just in case. After that came another one called Charles's law. And this one said that volume and temperature were directly related. So volume is directly related to temperature in this scenario. And you can probably see some real life experiences where this has occurred before. So for instance, when you open up a carbonated beverage, obviously the temperature is a little bit higher maybe than it was bottled at, than it was in the refrigerator at. And then when you open it, air blows out. That's because the temperature inside or the temperature outside has gotten warmer, and therefore the volume inside sort of gotten larger. That's one way of looking at it. The one that I think is easier to understand is, I know one night I had some balloons from like a birthday party or something like that, and it was the middle of the winter. I left them in the living room. They were actually fairly close to the fireplace, and when I got up next morning, they were like ginormous. And what had happened was the temperature of the room had heated the air inside of the balloon so much that the volume of the balloon increased noticeably. So that's Charles's law. So temperature and volume are directly related. Before we went further on, we came up with the Kelvin temperature scale. And basically, if you do a plot, let's say of temperature versus volume, it's kind of a neat thing that happens. You do a plot of temperature versus volume, and you can see that's going to be linear. That's what Charles's law suggests. But in fact, it's not exactly linear, because it lines up with a y-intercept. In fact, every gas you take, so if you say hydrogen gas, it'll be a line like this. If you take helium gas, it'll be a line like this. If you take water vapor, it'll be a line like this. If you take CO2, it'll be a line like this, so on and so forth. And what they discovered is all these lines are pointing back to the same spot on the line, on the axis. And in fact, that temperature seems to be the temperature at which their volume would be zero. And that became the ideal, the absolute zero of the Kelvin scale. So this became absolute zero. But it's interesting, because this is one of the times where if you meet another species from a distant galaxy even, you're probably going to have a very similar language you can speak with them, at least regarding the zero of temperature. you will find somewhere, if they're advanced enough to have any kind of science, space travel and stuff like that, you're going to find that they have a temperature defined as 0 that is exactly equivalent to our absolute 0 scale. And that's why in the temperature scales of Celsius and Fahrenheit, we use degrees, but in Kelvin, we don't. Okay. It turns out this is negative 273.15 degrees Celsius. So what we find is the temperature in Kelvin is actually equal to the temperature in degrees Celsius plus 273.15. Okay, so that's our formula for that. So we've got some new information that's kind of helpful to us. We found, in fact, that volume and pressure are inversely related. Volume and temperature are directly related. We found that there exists an absolute temperature scale. And since it's absolute, we don't have to use the degree. The degree mark really is a mark of randomness. Like we were free to choose a bunch of different things and we just arbitrarily chose a particular scale. So it's arbitrariness or randomness or something like that. That's what they indicate. Think, for instance, about why would you have the angles measured in the same thing that you do temperature, right? So I got degrees Celsius, I got degrees Fahrenheit, I got degrees angles, you know. Well, the reason why is because it was arbitrary. They could have chose any number to represent a circle. They chose 360 because it had a lot of nice, neat divisors. Okay. And by the way, the Celsius and temperature and Kelvin's or Celsius and Fahrenheit scales aren't really arbitrary. They're both based on water, but until, you know, fairly recently, when we got a really good hold on biology, it wasn't necessarily obvious that water was always going to be so important to life. But I suspect you might find, since water is probably very important to life, you're probably going to find a temperature system related to Celsius and Kelvin. I would suspect Celsius would be the smarter one, because why would someone start at 32 instead of 0? But anyways, there also turns out to be a equivalent to Kelvin. You know how Kelvin relates to Celsius? You know, one change of 1 Kelvin is the same as one change of 1 Celsius degree. Well, there's a similar scale for the Fahrenheit scale, and it's called the Rankine, R-A-N-K-I-N-E. It has the same size degree marks as Fahrenheit, but its 0 is way down below, you know, the freezing point of water, and is actually the absolute 0. So just to let you know that exists. I don't know anybody that uses it, so I'm not going to waste any more time on it. All right, the next law we have is called the Gay-Lussac law. Okay, and what Gay and Lussac found was this Gay, L-U-S-S-A-C law. What they found is that pressure is directly proportional to temperature. Okay, now each of these includes some caveats, and you probably already know them. That's why I didn't even take time to state them. But really, the volume is only inversely related to the pressure, assuming you keep the number of, or the amount of gas and the temperature of the gas constant. So in this case, N and T are constant. N being the number of moles, which you could also call as the number of atoms or molecules. Okay. And this one, of course, pressure and N are constant. And then in this one, you've got volume and N are constant. Now, you could say, instead of N, you could say mass in each of those, and that'd be certainly fine. But the main thing is you just got to know that these laws only held when they hold the other variable constant. And that's sort of the scientific method, right? When you're trying to figure out how temperature relates to volume, if you're changing the volume and the pressure each time, you're not knowing what effect occurs due to the volume change and what effect occurs due to the pressure change or whatever, right? So these were just methodical point-by-point experiments. Now, if you put it all together, what you find is that clearly from all this, you can see that P and V both being proportional to T, and P being inversely proportional to V, that suggests that P times V is proportional to T. And you might even realize, wait a second. If I fill this container up with more atoms are molecules of gas, then I'm definitely either going to increase the pressure or I'm going to increase the volume or both. So you can then reach the conclusion that pressure and volume are directly related to the mass times T. Ultimately, what we decided to do, at least in the physics and chemistry world, is we decided to use the number of moles. Okay. So ultimately what we got was the ideal gas law is PV equals N times R times T. And this R is a gas constant. Now, when you take steam table thermodynamics, you're probably going to learn that they're dealing, or at least some of the books I've seen, or every book I've seen, they use a different R for each gas. So it's actually R over the molecular weight of the substance is what they're treating as their R value. And because of that, you automatically just stick the mass in there and it spits out, you know, the number of moles basically. So we don't use that. We use PV equals nRT, and you can experimentally determine that R actually has the value R equals 8.314 joules per mole Kelvin. That's the one I use most often in physics. I remember in chemistry we used 0.0821, and that was liters times atmospheres per mole Kelvin. And I also remember on occasion using 1.99 in chemistry, and that was calories per mole Kelvin. Okay. So, of course, that begs the question, what the poop is ATP or ATM? ATM is 1 atmosphere. So let's get us calibrated. The pressure of the atmosphere on average is 1.013 times 10 to the 5th newtons per meter squared. Pressure is really a force distributed over a surface area. So you have to take the force in newtons and divide it by meters times meters for a surface area, and that's what the pressure is. Generally speaking, we expect it to be perpendicular, but there is a whole genre of using tensors where you can have pressures perpendicular and parallel components and all sorts of stuff. But we've now defined this unit to be the Pascal, so that's also 1.013 times 10 to the 5th Pascal. Well, that turns out to be 1.00 atmospheres. So there's another unit you can use. And of course, you can also see that there are other units you probably ran into, the bar and the torr and all that good stuff before. So I might as well give you some of those. For instance, yeah, I got 1 Pascal. Okay, a 1 atmosphere is 1.01325 is 1.01325 bar, which they abbreviate BAR. And that's also equal to 760 torr. I'll say here, 760 torr, which they abbreviate with TORR. And the one I like is 14.7 pounds per square inch. Okay, just because that brings it back to tire pressure. And that's, you know, I used to ride bikes, so that's like the only figure I ever knew about pressure. So I was always curious to know, well, how does this relate to the pressure in a tire? Well, your tire is flat if it's got 1 atmosphere in it, because 1 atmosphere is exactly equal to the pressure above it. So it can't sustain the weight, it can't sustain the contraction of the metal, of the rubber or any of that kind of stuff. So in fact, you need 35 psi, or in some cases it goes up to like 55 for different types of tires. So anyways, that's our units. And one of the first problems that you normally work when you introduce the ideal gas law, and you introduce the units of pressure, one of the first problems you usually work is something called, what is the volume of a gas at STP? So here's another example. Example 3. What is the volume of an ideal gas one mole, that is, at STP. So that begs the question, of course, what the poop is STP? Well, you probably already know it. I hope you do. If you don't, I'm going to tell it to you now. Standard temperature and pressure just means 0 Celsius and 1.00 atmosphere. So STP implies T equals 273.15 Kelvin. And by the way, as you can tell from these units in here, the temperature has to be in Kelvin when you use the ideal gas law. And then the pressure is equal to 1.00 atmosphere, which again is 1.013 times 10 to the 5th Pascal. So if I take PV equals nRT and solve for V, then I get V is just equal to nRT over P. So I'm going to put in 1.00 mole times 8.314 joules per mole Kelvin times 273.15 Kelvin over 1.013 times 10 to the 5th Pascal, which again is a Newton per meter. So you can see the joule is a Newton times a meter. So when I divide it by a Newton over a meter, I end up getting the Newtons canceling out and I get meters squared up top. Okay. But I also have a mole canceling out with a mole, and I also have a Kelvin canceling out with a Kelvin, and ultimately, oh, it's meter squared. Sorry about that. You end up having a meter cubed on top because it's meters squared down here. So this Newton stays in the bottom and the meters squared go up top. The Newton down here cancels out with the Newton meter up here. So the meter times the meter squared gives you meters cubed. And lo and behold, what you get is a very typical classical result that's often talked about all over. So it's 22.4 times 10 to the negative 3rd meters or cubic meters. But what you know is a liter, 1 liter, is defined to be basically a 10 centimeter by 10 centimeter by 10 centimeter volume. So it's a cube 10 centimeters on a side like that. So 1,000 cubic centimeters. So this actually means that this is 22.4 liters. Okay, you can do that conversion yourself, but that should be pretty straightforward. So that's something we can make use of from time to time. If you ever want to know roughly what the volume of 1 mole of gas is at 0 degrees Celsius and standard atmospheric pressure, it should be 22.4 liters. Any questions on that? So you can see a lot of this ideal gas law stuff is really pretty straightforward. We'll use the ideal gas law. Of course, you've got to be able to calculate the number of moles. Hopefully y'all remember how to do that. But the main thing is remember that if you take the mass of the gas that you're using and you divide that by the mass per mole of that particular atom or molecule, then you get the number of moles. So that's the key rule there. N is equal to M over M atomic, say. Okay, so this is grams per mole. This should be in grams, obviously, when you go to do it. But when you divide it by grams per mole, then you get a number of moles. And you got to do stuff like CO2. That means carbon is represented 1 time, and then oxygen is represented 2 times. So you take the mass of carbon and add it to 2 times the molecular or the atomic mass of oxygen. Okay, so just keep that in mind. I think y'all hopefully had enough experience with that already to know how to do that stuff. If not, the examples in the book are there, and you can always ask me, of course. That's what I'm here for. This is why I get paid $250 million a year. Yep. Any questions on that? All right, let's do another example. Example 4. Okay, in this case, I'm going to imagine a helium-filled party balloon is a perfect sphere. Now, that doesn't look like a perfect sphere, but I'll tell you it is. Okay, and in reality, it's probably more like this with a little knot and stuff like that. But I'm going to say it's a perfect sphere, and I'm going to say its radius is, in fact, what did I choose before? I said 12.0 centimeters. And I'm going to say that thing is at a temperature of 20.0 degrees Celsius. And I'm going to say it's at a pressure of 1.00 atmospheres. And what I'd like to know, if it is filled with helium, then how many moles of helium are in it, and how many grams? Whoa. See, I say the word grams and my A becomes a G. I swear it's like something wrong with my brain. So how many grams of helium? Okay. So we're going to use the ideal gas law. The ideal gas law says PV, and I'm having a hard time writing it this way. I'm used to writing it where the P is lowercase, the V is uppercase, the N, the R, and the N is lowercase, but the R and T are uppercase. There's a reason for that. When y'all get to thermodynamics, you might actually learn that there's a good reason for using a lowercase p versus uppercase V. And we actually use a lowercase v for a very specific thing as well. So just keep that in mind. Later, when you see people using different size letters, they're trying to do a very specific thing, and you need to know about that. Okay. So with PV equals nRT, we can obviously see that N, the number of moles, is just equal to RT over PV. Okay. So R is 8.314 joules per mole Kelvin. Now, can I use the 20.0 degrees Celsius in this equation?
No, you have to convert to Kelvin.
Exactly. So I just want to make sure everybody recalled me saying that. 293.15 Kelvin is what we have to use there. And then the pressure, can I use atmospheres? I didn't explicitly say this. There is a way you can use atmosphere, but you can't use 8.314 joules per mole Kelvin to do it. Joules got Newton meters in it, right? So you've got to convert this to 1.013 times 10 to the 5th Pascal, which you remember is newtons per meter squared. And then the volume is going to be 4/3 pi times the radius, which is 0.12, 0.1200 meters cubed. Okay. You guys need to verify this calculation yourself. Make sure I didn't do something boneheaded, but there's a high probability I squared it instead of cubed it or whatever. So make sure you check that out. Oh, I was looking at work. Gotcha. Okay. So hopefully this is what you got to 0.09576. This is a 0 here. That's what I get for the number of moles. Now, if I carry this out, that's 4 sig figs, that's 5 sig figs, that's 4 sig figs, that's 4 sig figs. So everything should be able to go to 4 sig figs. So I'm happy with that. Actually, there might be another digit, but I chose not to write it down. So anyways, there's probably another digit after that. It would be good to write down for subsequent calculations, but I'm going to leave it at that. So there's one of our answers. That's the number of moles. So basically, what, 96 thousandths of a mole? Now, in order to figure out the mass, we're going to use what I told you earlier about how to compute the number of moles. The number of moles is equal to the mass divided by the molecular weight. So the mass is equal to the number of moles times the molecular weight. So I'm going to say 0.09576. And this is the perfect chance for me to show you exactly how we use that extra digit. So I'm going to go ahead and pull up in my calculator and see what that extra digit was. 95762. Okay, and that's moles. And then I looked up the molecular weight of helium. Helium is not diatomic like hydrogen, nitrogen, and oxygen are. It just does its own thing. It's a noble gas for starters. And it is 4.0026 grams per mole. That's a unit you can think of when you look at the periodic table. It's really helpful to use it that way when you're dealing with this kind of stuff. However, it's also helpful to use it as the atomic mass unit, the universal atomic mass unit, when that's necessary. So remember, this can be thought of as grams per mole, but it can also be thought of as U, the unified mass number, which is literally like the mass of this atom, or for helium's case. And when you do CO2, it's the mass of that molecule. So there's two ways of looking at it. Now you see the moles cancel out here. And when I multiply that by 4.0026, I get 0.393. 39330 grams, and we should have 4 sig figs. So 1, 2, 3, 4. That's one extra sig fig there. Okay, if you want to convert that to kilograms, you'd have to move the decimal 3 places to the left. So it's really a small amount of mass. And that was the main reason I wanted you to do it, just to have some feel for how much quote unquote air or helium weighs filling a balloon. The more typical problem, and I'm actually getting ready to do that in a second, is to think about the weight of the air in a classroom. A big classroom like 30 feet by 30 feet by 9 feet. How much is that? So that's the next problem we're going to solve. But does anybody have any questions on this? Negative. Okay. One thing I used to do is I realized that the density of water is 1,000 kilograms per cubic meter. And the density of air, on the other hand, is like 1.27 grams per cubic meter. So that's one way you can always do this sort of thing. But in this case, we're going to do it with the ideal gas law. So we're going to say example 5. What is the mass? What are the mass and weight of the air in a classroom? Now, this is a very good problem for me to ask you in general, like if we were just doing a face-to-face test. And I'd say for the classroom that you're in, because it would actually require you to estimate the sizes. But in this case, I'm just going to give you the size of the room that I want you to consider. And in this case, I'm going to assume it's about 30 feet by 30 feet by 9 feet. So that's going to be 10 meters by 10 meters by 3 meters. So what we want to know is M and mg. Okay. In order to know that, of course, we need N, right? That's the way we get that out of the ideal gas law. So we know N is equal to R times T over P times V. So that's 8.314 joules per mole Kelvin. I'm going to assume it's 20 degrees Celsius. So that's room temperature, basically. Assume T equals 20.0 degrees Celsius. It's actually a little colder than room temperature, but anyways, so that's 293.15 Kelvin. I'm going to assume the pressure is 1 atmosphere, so that's 1.013 times 10 to the 5th Pascal. And we already work out how this works out to moles. But 10 times 10 is 100 times 3 is 300. So this is 300 cubic meters for the volume. Okay. So when I do that, I do 8.314 times 293.15 divided by, make sure I put parentheses around it, 1.013 e to the fifth times 300. Because if you don't put parentheses around it, it's going to multiply the 3 times the top as opposed to the bottom. So with this, I get 0. This can't be right. Oh, yeah, I typed something in wrong. No, maybe not. Let's check out my unit. It says Joule is a Newton meter, Pascal is a Newton, so that gives you a, oh. Okay, I see, I just stole something I wrote above it. Anybody see the error on my page? There's 2 of them now because I stole it. If I solve that for n, what the crap did I do? This is terrible because I worked it out before and didn't even notice it. That's horrible. Oh my God. I hadn't worked out the air one. The balloon one seemed reasonable to me, but in retrospect, not so much. Notice if I solve for n should actually be PV over RT. What the heck is wrong with me? So no. Let's say raise this to the -1 power. And let's say no. And now I'm going to put the correct answer right there. I'll do that for you real quick, everybody. Sorry about that. Basically, I'm going to take that 0.095762, and I'm going to take 1 divided by that because it looks right other than that. So I'll do 1 divided by, now I'm going to scroll up there and hit enter. So now this looks more like what I should have gotten. I really did not expect that many moles to occur, but can someone verify that this is actually 10.443 moles? So let's double check all my units. This is actually going to give units of reciprocal moles, as I should have seen from right there, stupid head. So if I'd done the unit analysis that I did on the last problem, this wouldn't have happened. Now I'm going to, just to make sure, I'm going to do it using the proper numbers. This times this divided by this times this, just to double check that if anybody's verified already, you can save me that step.
Confirmed.
You did confirm? Okay, thank you. Appreciate that. So this is the correct answer, not the stupid number that I got before. So hopefully that says no, good enough. Same thing with this one. Since I used that result, this is a no. And this is a no. So this number is going to become 10.443. And I used basically 4 sig figs everywhere. So this is the extra sig fig. That's the extra sig fig. So now I've got that. I'm going to say 10.442 times 4.0026. And that gives me 41.797. 41.797 grams. I really didn't expect it to be that high, but I definitely thought it was kind of weird that it was lower than a gram. But anyways, that's what that turns out to be now, using proper units. Hopefully someone can verify that as well. And now on this one, I'm going to again say no. Say it's this to the -1 power. What I'll say is N is equal to 1.013 times 10 to the 5th Pascal times 300 meters cubed over 8.314 joules per mole Kelvin times the temperature 293.15 Kelvin. So let that be a lesson. Don't let distractions get you. So I'm going to say 1.013 e to the 5th times 300 divided by 8.314. And now I'm going to do divided by again 293.15. That's another way you can do it instead of using parentheses. And I get 12.4690. And this one does work out to be moles. Notice I got moles in the denominator, so that means moles on top. And the joules cancels out with the Newton part of this, and the meter cubed cancel out with the meter squared under here, and the meter that comes up from there, and the Kelvin cancels out there. So yes, this does give me proper units of moles. So I now have one answer that they asked for. Actually, I do not have an answer they asked for, but it's something that we need. So I do have that. I'm going to box it off anyways. What we did ask for was how many grams. So M is equal to 12.4690 moles of air. Now, basically air is 20% oxygen and 80% nitrogen. Really, to be honest with you, all the other ones, argon, for instance, is the highest, and then water vapor, I think, is the second. No, CO2, and then water vapor, and then CO2 is the next biggest. But all of those add up to less than 1% roughly. So there's no need to do that. So what I'm going to do is I'm going to take 0.20 for oxygen. And of course, the molecular weight of oxygen, and I am saying molecular because it's O2 is the way oxygen appears in our atmosphere. That's O is 15.9994, so I'm going to call it just 32 grams per mole. And then I'm going to say plus 0.80 times nitrogen. And of course, nitrogen, I think, is 14. Yes, nitrogen is 14.0067. So I'm going to say 28.00 grams per mole for nitrogen. And then that's what I'm going to use as my molecular weight. Does everybody understand that? Air is a mixture. It's not a compound, but it's a mixture of compounds. So you do the molecular weight of one of the compounds times the percentage that it exists in that mixture, and then the other one the same way. So with all that in mind, I'm going to take that number 12.46 whatever times parentheses 0.2 times 32 plus 0.8 times 28. Like this, and say enter, like that, and I get 359 times 10 to the 3rd. So it's 359.11 times 10 to the 3rd grams. So that's really 359.11 kilograms. So that's pretty significant weight already. And that's sort of why I do this, is let you see how heavy the air in a room is. Now, if I want to know the weight in newtons, I could, of course, also do this in pounds, and it would make it a little bit more sense to you. So just for fun, I'll multiply that by 2.2 pounds per kilogram. So I'll say times 2.2, and you see that's about 790 pounds. So yeah, nearly 800 pounds of air in the room. Now let's do the actual weight. So that's M times G, which is 359.11 kilograms times 9.80 meters per second every second. So I'll take that times 9.8. And lo and behold, I get 3.519 times 10 to the 6th newtons. So yeah, 3 million newtons. Any questions on that? We're supposed to go to about 12:15. We've only done up to 12:02 right now, and I'm virtually done with the chapter. There's a little bit more I need to cover, but that's some good examples of how to use the ideal gas law. Now, there's also a wonderful scenario that can happen where you can use the ideal gas law a lot easier. So for instance, if they take a set amount of gas, let's say you do something like someone tells you, okay, we have a balloon, it's filled with air, right? And you say, right now the pressure, volume, and temperature is blah. And you say, okay, what if I raise the temperature? What's the pressure going to be now? What's the volume going to be now? Stuff like that, right? Well, you don't have to go all the way back to the ideal gas law. You just have to realize, wait a second, I'm using the same sample of gas. So the N is not changing. The number of moles is not changing. Of course, R is a constant, so that's not going to change. So we have this whole other process by which you can use a different form of the ideal gas law. And it, in some sense, is more correct than the ideal gas law because the proportionality is not exactly 100% true in the ideal gas law. We, for instance, have the van der Waals equation and stuff like that because it shows that at extremely low temperature, the molecules tend to get close enough together where molecular forces pull them and make them, come together, and where their actual size becomes so relevant that you have to take that into account in the volume. So those sort of things give you a slightly more accurate version of the ideal gas law, and they're real everyday life applications where you might use that is if you're scuba diving, for instance, with Heliox or Trimix or one of those things, or Nitrox. Those are various things you can use to breathe in scuba diving. And they have advantages, like using Heliox, you actually have helium in you instead of nitrogen. And the nitrogen is actually what gives you the rapture of the deep, which is supposed to mean, sort of your drunkenness of the deep, because nitrogen actually becomes like a sedative or like an alcohol type thing when you're at depth. So if you take out all the oxygen and replace it with helium, then you can actually go down quite deep and not get narked, not get drunk. So if you're, diving the Monitor, which is like 230 feet of salt water, you'd be pretty punch drunk. It takes a lot of practice to dive at 230 feet and not, just do something stupid and kill yourself. So that's why you can't just go diving that after your open water 1 scuba certification. So that's one thing. But the disadvantage, of course, with that is that helium turns out to be a little more sticky to your platelets. So you actually have to spend a lot more time on ascension to basically decompress, because otherwise the helium will come out in solution just like the nitrogen does when you get the what we call the bends. So the helium has that problem, but it has the nice effect that it doesn't get you drunk. Then there's nitrox, and nitrox allows you to increase the nitrogen decrease the nitrogen, but increase the oxygen, so that again, you're a little less drunk. But by upping the oxygen level, there's a level at which oxygen becomes toxic. You start having seizures, and that's suboptimal, of course, when you're underwater. Seizures and vomiting, things like that, are not good, right? So, anyways, when that happens, that's a problem. So they decided to start mixing oxygen and nitrogen in various amounts, and then as long as you're going above a certain depth, then you're fine. But in order to make all this science work out, you actually can't use just the ideal gas law. You have to use van der Waals equation a little bit. So that's kind of neat how that comes in. So anyways, with that in mind, I want to jump to the new version of sort of the ideal gas law. And I say it, with parentheses around it, or with quotation marks around it, because it's really not just the ideal gas law now. It's sort of more real because it's Charles's law, Gay-Lussac's law, and Boyle's law. But basically, if you look at PV equals nRT, you can see that nR is equal to PV over T. So that PV over T is really a constant for a given sample of gas. Because of that, you can now use P1 V1 over T1 is equal to P2 V2 over T2. Later, we'll get even more versions of this, for instance, for adiabatic processes and stuff like that. But for instance, if the volumes don't change, you don't have to put those equations in. You'll get P1 over T1 equals P2 over T2. Or if the temperature doesn't change, you can just do P1 V1 equals P2 V2. Or if the pressure doesn't change, you can just say V1 over T1 equals V2 over T2. So that's a whole nother way of using the ideal gas law. You'll see some examples of it in your book. I think they're really remedial and not necessary to sort of explain to you, but just remember your temperature's still got to be in Kelvin. That's the main thing, because Kelvin is one of those ones where you convert by addition. So just using, Fahrenheit or Celsius is going to be a problem, because they don't just cancel each other out. It's not by multiplying Celsius by some number do you get Fahrenheit, or by multiplying Celsius by some number do you get Kelvin. So because that's not a multiplicative transformation or conversion, then it's not going to just cancel out and work. So you always got to use the Kelvin. But other than that, this equation is good to go. Now, the other thing I wanted to show you about the ideal gas law, and this is the last part, and we're finishing off the chapter now, is basically PV equals N times R times T. Well, we know that really the number of moles is a count, if you will, of the number of molecules, or in the case of a pure element, the number of atoms. So it actually equals the number of atoms divided by Avogadro's number. Well, it turns out there's another constant you can use instead of R, and that's R over Avogadro's number. And you end up getting PV equals the number of atoms or molecules, that's what the big N stands for, times KT, the Boltzmann constant, where KB equals the Boltzmann constant, which I seem to recall is 1.2807 times 10 to the 8th or something like that. So basically what you're going to do is say, well, I know that's R over Avogadro's number, and that would be 8.314 joules per mole Kelvin divided by 6.022 times 10 to the 23rd items per mole. So I'll just write moles to the -1 here. Obviously, the mole to the -1 in the denominator with the mole to the -1 in the numerator is going to cancel out. And all I get left is joules per Kelvin. And that's not what I remembered. I'm going to look up the Boltzmann constant in the back, because I might have done something funny with my calculator. The Boltzmann constant is 1.3807. Yep, that's what it was. I was remembering the 2. It's 1.3807. The 1.3807 times 10 to the -23rd. Joule per Kelvin. Okay, so that's our new constant that we can use in place of R. But if we're doing that, we have to put in the number of atoms or molecules. Again, that doesn't seem so neat, but later when we do kinetic theory, we're basically going to treat individual atoms and molecules as if they're billiard balls having perfectly elastic collisions. And upon doing that, we can more or less derive the ideal gas law, and we get a derivation of the average kinetic energy of a molecule or atom for a given temperature. That actually allows us to find the internal energy of a sample and all sorts of good stuff. Again, for ideal gases, and they turn out to be fairly precise, even though it's the ideal gas law. So any questions on that? All right, I'm going to check chapter 17. I think it's perfectly reasonable for the concept questions for chapter 17 to be due tonight. So if they're due tonight, they're going to be due tonight. Okay. But if I find that I made the actual calculational problems due tonight, I'm going to fix that and push it back to Sunday.
Understood.
Is that cool?
Yes, sir.
All right. Well, y'all have a good one, folks. And hopefully everybody did your test. Remember, you have a test that's due tomorrow too. So make sure you don't miss that. And other than that, everybody's free to go.
You have a good day.
You too.
I'm good.
See you, Clarence. Let me know if you have any questions. I'll wait here for the last one to leave.
I sent you an email. I don't know if you saw it or not yesterday about not being able to access the homework, but I checked it this morning and now I'm able to. So
Now you're able to.
I'm not sure what was wrong, but
yeah, I've had some of that problem sometimes when I go on mastering. I don't know if they just don't have enough bandwidth, but sometimes it just won't let me log in. It says it's unavailable at this time, and they need to get that crap fixed. So
yeah,
I
was on question 5. I hit next question and then just kicked me out for the rest of the day. I was like, okay.
That sucks. When you do that, if you're like close to a deadline, make sure you take a screenshot of it and record the time and send me an email immediately. That way I can give you an extension without being unfair to other students.
Okay.
Okay.
Thank you.
No problem. See you, Aiden.
I just wanted to double check that it's test 5 due tomorrow night.
Yes.
Okay.
Yeah, the 4 was due Sunday and 5 is due tomorrow night.
Okay, cool. Just wanted to make sure.
No problem. Have a good one. Kendrick, Patrick, Vanessa, Emil, anyone? Bueller. I need all y'all to go home and watch Ferris Bueller's Day Off. Pretty in Pink, got to watch that too. Breakfast Club, yep. St. Elmo's Fire, all those. Y'all got to go watch all those. And then catch up on the last 25 seasons of The Simpsons. All right, have a good one, everybody. Bye-bye.